Right, I'm sorry this is going to be an extended tutorial. Like, we normally have fun in these good times. The physics banter is still there, I trust you, with this blue pen from Staples. Enjoy. Okay, so if it hasn't creeped you out enough yet, we're going to start some creepier physics. Yes, it gets more intense, ladies and gentlemen. Take your seats. Take your seats. Okay, so what we're going to be doing today is we're going to do a bit on potential dividers. You may be asking me, well, what is a potential divider, Will? Well, good question, Will. A potential divider is basically like a variable resistor, except you have two of them, yeah, in a series. So, when it comes across, when you look on the exam, as something like that, but it's just two resistors joined together, and this allows you to turn it all the way down to zero, but it's very time consuming and expensive to put in a circuit. You've got to know where to put it, so your employer might need some training on that. So, yeah. So, to supply a fixed PD, so I just put fixed PD, so one that doesn't change. To supply a fixed PD, let's give us a I was going to say a graph then, circuit. We've got two resistors, we've got R1 and we've got R2. Now you should know from your studies that you can, I'm going to show you how, obviously I'll do that in another video, but R is equal to R1 plus R2, so you just add up the resistance to get the total resistance in the circuit. Yeah, so we know that. So this is R, basically. We know that V equals IR. And we can arrange this to get I. So we put V over R. And obviously V, as we said, you can add, well, we didn't say this, but you can add them up. So, you know, V1 plus V2. And again, that's another video. So I equals, so you can add the V's up. So V1 plus V2, use your total V's, and then R1 plus R2. That's your total resistance in the circuit. Yeah, so, yeah, one sec. I don't think I've missed anything out on that bit of the tutorial there. Yeah. Proportional to this source PD squared. I don't think there's much to it. I mean, I might have looked at this a bit differently to what you should do. But a fixed PD is just one that doesn't change, so you just use your general formulas for that. Variable PD? Ah, this is the one I was worried about. Well, not worried about, because it needs a bit more explaining. That's why I spent a few minutes on that, trying to figure out if I'd got everything. And for a fixed PD, it's quite simple. You just use your already known equations. Now, a variable PD, as it suggests, you can change it. And this might be useful in different scenarios where it's required, obviously. So, one sec. Yeah. I'll do a quite simple one. So this is where you've got a contact. I'll just draw a simple diagram, and then you might go, what's that extra lining? The quick and narrow? Well, that is what we call a sliding contact. So, just going to put sliding contact. Here you go. Why do we need that? Well, again, this proves why you can denote it to pretty much zero resistance, because you can get rid of the resistance. You can move this all the way over here, you can put it here, so you're missing out the resistor entirely, so you can turn it to zero, as there won't be any resistance to bring light into your fair world. Good sir, good sir, good sir, good sir indeed. So, yeah, sliding contact. That means you can move it, you can increase it or decrease it depending on which terminal you're going it towards. Now, that is pretty much it that you need to know, but obviously, you being me, and you being you, and this being a whiteboard, we're going to add some more to the crazy stuff. So, you may get asked to draw certain circuits. So, yeah. We'll do a temperature sensor first. So you've got your cell. No. You need a. What's that? Oh, so just one of these. It's a fixed sort of resistor, that I think. It's not very good, that. And then we've got a thermistor, which is a bit like a hockey stick one. And then you've got your voltmeter. Just put V. Now, you may go, well, what is that? Well, it's a temperature sensor, because the thermistor increases temperature, and it's got a positive temperature coefficient. This means the metals inside the resistor vibrate as the thermistor, the surrounding temperature increases. So this tells the voltmeter, oh, the electrons do more work to get through. Here you go. There's more potential difference, so voltmeter increases, and this tells you it's getting hotter, which could relate to given electrical instruments inside, for example, your car, and it would say, yes, this is definitely getting warmer outside, so it'll relay that information to the car, put through that car's brain, the CPU. Sorry, I'll go off that, I was going off physics. So that's just an example of a use. So, and then we could have a light sensor. So exactly the same sort of thing, except we're just replacing. Again, you're going to like to have a battery there. So you've got your resistor here, and you've got, instead of a thermistor, still got a voltmeter here though. We've got a LDR. Now, an LDR is something that increases temperature. No, increases light, sorry. So the more light, the more resistance, the more work done, the more energy transferred, the more. Which is all means the same thing, but it only contributes to the higher voltmeter reading. Hopefully that's given you a bit of a guide to potential dividers, but generally, on the whole, I think we've covered pretty much everything. So we'll see you in the next video.